Hi students, today we are going to learn about conductivity in nerve fiber. What is the meaning of conductivity? Conductivity refers to the ability of cells to transmit electrical impulses. Okay, so what is conductivity? It is the ability of the cells to transmit the electrical impulses. That is propagation of the nerve impulse in the form of action potential. That is a wave of depolarization throughout the nerve fiber. It occurs in both myelinated and non-myelinated axons. So, okay. So, how it happens? It involves these steps or these mechanisms. So, the propagation of action potentials in the nervous system involves local current loops. Okay, first one is the formation of the local current loops. So, for explanation of the uh, conductivity of the electrical impulse in a axon, it is suggested is based on these models. So what is the first model? It is forming local current loops. Second one is the equivalent circuit model, and the conductivity is also depending upon the cable properties of the membrane and properties of the cytoplasm. They will determine the velocity of signal propagation, and also the velocity of the signal propagation depends upon the myelination of the axon. Myelin improves the efficiency with which axons can conduct the action potentials faster. See this? This is the first mechanism. That is the propagation of action potentials in the nervous system by forming local current loops. This is unmyelinated axon. This is a myelinated axon. In this unmyelinated axon, if you stimulate here, what is happening? This is becoming active zone. Then depolarization is happening at this point. Then this is forming a local loop of current. Okay, this is forming local loop of current. And in this myelinated axon, myelin sheath is present. It is uh, having some gaps. So between the gap of myelin sheaths, we have nodes of Ranvier. So at the node of Ranvier, there is formation of local current loop. Then coming to the second model, that is equivalent circuit model. This model is given by Hodgkin and Huxley. So what this model is suggesting? This is a lipid bilayer. So this lipid bilayer, it itself acts as a insulator. Okay, so this lipid bilayer will act as an insulator, which is approximately 10 nanometers in thickness. And the electrolytes which are present inside and outside the lipid bilayer, they are regarded as capacitor with a capacitance of Cm. So this is Cm. So they will act as a capacitor with a capacitance of Cm. Then transfer of electric charges which are penetrating the membrane is expressed as an electric current. Okay, so here you can see sodium is penetrating to inside the cell, potassium is going outside the cell. They will create or they will generate electric current, and this is stopped by specific ionic resistance, okay, and a specific potential. So because of the resistance and because of some potential difference, the flow stops at one point. Okay, so this is an unmyelinated axon. So at each and every point there will be formation of a electric circuit. This is called equivalent circuit model. Here, the generation and conduction of an action potential on the surface of axonal membrane has been described as a physiological electric circuit known as an equivalent circuit model. So, physiological electric circuit will be formed. This fundamental circuit model was first introduced by Hodgkin and Huxley. In this model, movement of an electric charge penetrating through the membrane, it is described as parallel alignment of conductance for each type of ion. So, in this model, what is said? The movement of the electric charge penetrating through the membrane. So, how the electric charge is moving from outside to inside and then inside to outside. So, this electric charge movement is parallel to the conductance of each type of ion. So, potassium is moving inside, that is conductance is like this. Then sodium is moving inside, conductance is like this. And it is creating electric charge through it. And potassium moving outside, it is also creating electric charge. So the movement of electric charge is parallel to conductance of the ions. Now coming to the cable theory. Cable properties of the membrane and cytoplasm. See this cable theory. The mathematical models were proposed by William Thomson in 1850 and by Hermann in 1870 and by Hodgkin and Cole in 1920 to 30. Okay. In axon, it was given by Bernard Karch and many other scientists also worked on this theory. It is on the basis of equivalent circuit model. Okay. Here, the conduction of the nerve inside the nerve is described as like this. It is regarded as an electric current on imaginary electric longitudinal leads. These leads are running inside and outside the axon membrane. This is known as cable theory. So this theory is saying, electric current, okay, electric current is running on imaginary electric longitudinal leads, and these leads are running inside and outside the membrane. Okay. So coming to cable properties. So these are the properties of the nerve, axon, cell body and dendrite. Okay. And affect the distance and the speed of membrane potential. Why these are important? Because these properties will affect the distance and the speed of the membrane potential change. These are called passive properties. These are passive conduction properties. Okay. Because of these properties, you can see the signal becomes reduced over distance depending upon the cable properties. See here, passive flow of current. Suppose it is a copper wire or a neuron. Okay. This is a stimulus. Here we have given a stimulus, that is site of depolarization. Then what is happening? Here in both directions it is traveling. So while traveling, because of the cable properties of the neuron, depending upon the time and distance, the speed and the distance to up to which it is reaching is decreased. So when compared to small unmyelinated neuron and a large diameter neuron or a myelinated neuron, which is better? The myelinated neuron is having better flow of depolarization. So it can travel up to more distance. Okay. So here current is shown as I. It is the amount of charge moving past a point at a given time. So current I means charge moving. This is a function of a drop in voltage across the circuit and the resistance of the circuit. So voltage is the energy carried by a unit charge. Resistance is the force which is opposing the flow of electrical current. So you know that resistance is a opposing force. Voltage is the energy carried by a unit charge. Current is the amount of charge which is moving a point in a given time. So this is the passive cable properties of an axon. So you have stimulated here. So these are studied in the better studied in the unmyelinated axon. You have injected a stimulus. Then you see this, there is a signal decay. The decay is exponential. So there is exponential decay of the signal, or the voltage is decaying. Okay, voltage is decaying. This is lambda. We will come it later. Here you can see the same thing. Voltage decreases with the distance. Okay. So there is decremental conduction. Why it is happening? It is happening because of the resistance. Okay. So here you have three resistors. Three types of resistance is there. So each axon, each area of the axon consists of an electrical circuit that you know, and it has three resistors. What are those three resistors? Resistance in the extracellular fluid. If there is high resistance in the extracellular fluid, there is increase in the decrement. Then coming to the cytoplasmic resistance, that is intracellular fluid resistance. If there is high resistance, then also it leads to increase in the decrement. Then coming to the membrane resistance. Okay, membrane resistance. If there is high resistance in the membrane, there is decreased decrement. Okay. Potassium channels, leaky channels, which are always open. Okay, some positive charge leaks out. It leads to decrease in the current. And few potassium leak channels decrease the positive charge leak out. If they do that, they will cause high membrane resistance. So here you can see three resistors, that is intracellular fluid, extracellular fluid and membrane resistance. Okay. This is extracellular fluid, this is membrane, this is cytoplasm. And this is again membrane, this is extracellular fluid. This is an electric circuit model for axon. This is a patch of the membrane. If you see, it is like this. This is the resistance of the extracellular fluid, capital R, small e. This is resistance in the membrane, capital R, small m. This is resistance in the cytoplasm, capital R, C or I. This is capacitance. What is capacitor? Cm, capacitor. It stores the electrical charge. So what is mean by capacitor? It can store the electrical charge. Okay. Two conducting materials are there, ICF and ECF, and you have an insulating phospholipids, that is in the membrane. Okay. So we have connecting materials in the ICF and ECF, and you have an insulating layer of phospholipids in the membrane in between them. So in between them you have a capacitor. So cell membrane acts as a capacitor. It stores the electrical charge. Loss of current across membrane. How it occurs? Loss of current across the membrane through leaky channels or rest channels. Okay. So loss of current across the membrane results in dropping in the membrane potential. Okay, and it is depending upon the internal resistance and the membrane resistance. The length or space constant, that is lambda, describes this property. This lambda is a distance, that is in millimeter, at which V is equal to 1 by E VO. or the distance at which V has decreased to 37%. So lambda is a distance at which V, that is voltage, has decreased to 37%. The formula is V is equal to 1 by E V 0. The relationship between the voltage at any distance, that is x, from the applied or original voltage is, so what is the relationship between the voltage and the distance, that is Vx, voltage at that particular distance, is equal to voltage 0 or voltage O, that is the initial voltage, into E to the power of minus x by lambda. Then coming to loss of current due to capacitance properties of the membrane. Actually, the cell membrane acts as a capacitor. Okay. We have already seen that ICF and ECF are conducting material. It is separated by our insulating cell membrane. That lipid bilayer, which is 7 nanometer thick, and it can act as an excellent capacitor. It takes time and current to charge the membrane capacitor. So we want some time to be given, and we need to give some current or charge to charge our membrane capacitor. As current drops over the length of the nerve, takes longer and longer to charge the capacitor. So if the length of nerve is like this, at starting point, that is at which you have given stimulus, at that point we can charge the capacitor very fast. If you go away from the depolarization site, it takes longer time to charge the capacitor. So the time constant, this word will describe this effect. So time constant is capital Rm into Cm. So it is the time taken to reach 63% of the final voltage. It is expressed in milliseconds. The time constants ranges generally from 1 to 20 milliseconds. The smaller the capacitance properties, the less the current loss and faster the nerve impulse travels. So we need to have smaller capacitance properties and less current loss to ensure faster nerve impulse travels. The larger the capacitance properties and more current loss will cause nerve impulse to go very slowly. So this Rm, that is membrane resistance, is inversely proportional to surface area. That is, if the area is more, that is in larger diameter fibers, there are more leaky channels. So there is less resistance of Rm. And Ri is inversely proportional to the volume. That is, in larger diameter fibers, there is more volume, there is less internal resistance. Effect of resistance on conduction speed. If Rm is low, lambda is low. So conduction speed is also low. If Ri is low, then lambda is more. Then there is more conduction speed. They do not cancel out each other. Okay. Rm is proportional to radius. Ri is proportional to square of the radius. Therefore, the net effect of increasing the radius of the axon will increase the speed of conduction. You see this conduction speed, this is a smaller diameter axon, this is a larger diameter axon. Here the lambda is 0.7, here lambda is 1.6. Here we have larger conduction speed. Then coming to the speed of conduction and capacitance. So we have seen the speed of conduction with the resistances, that is membrane resistance and internal resistance. Then we came to speed of conduction and capacitance. That is about the cell membrane capacitance. The capacitance is the quantity of charge needed to create a potential difference between two surfaces of a capacitor. So that much charge is required to create a potential difference between two surfaces of the capacitor. It depends on the three features. Okay. Material properties, generally same in all cells, and it depends on the area. That is, increase in the area leads to increase in the capacitance. And it also depends on the thickness. Increase in the thickness leads to decrease in the capacitance. Okay. Then we have talked about lambda. Now we came to time constant, tau, speed of conduction and capacitance. In this we are talking time constant. This is the time needed to charge the capacitor. We need to charge the capacitor. So how much time is needed to charge the capacitor? That is given by time constant tau. This is equal to Rm into Cm. That is membrane resistance into membrane capacitance. Low Rm or Cm implies low time constant. So the capacitor is filling fastly. So conduction is faster. So for a faster conduction, you need less time constant and more length constant. Okay. The conduction speed, we can increase it by myelination and increasing the diameter of the axon. Okay. So they have given conduction velocities in axons from various species. So as the diameter is increasing, the speed of conduction is increasing. And with the myelination also, the speed of conduction is increasing. Coming to the diameter of the axon. Increase in the axon diameter increases the velocity of the action potential. We have seen that the velocity is a 1 mm in 1 mm diameter of the giant squid axon. It is having very huge velocity of conduction. Okay. Why does increase in the diameter of the axon leads to increase in the speed of the conductivity? Here you see Rm, Ri and Cm all related to the radius of the fiber. How? You see Rm, that is resistance of the membrane, is related to half into pi into radius. Ri, that is internal resistance, is related to 1 by pi into square of the radius. Cm, that is capacitance of the membrane, is depending upon the radius. So, increase in the diameter of a fiber, what it causes? Internal resistance decreases and membrane resistance decreases. But internal resistance decreases faster. Therefore, there is a benefit observed. Okay? Observed. This causing faster conduction in the action potential relative to the membrane resistance. Therefore, the distance that membrane potential can travel is increased by increase in the axon diameter. So, what he is saying? So, they are relating to radius only. But Ri decreases faster because it is depending upon the 1 by pi radius square. That is, it is inversely proportional and square of the radius. So, if the diameter is decreased, diameter increased. If the diameter is increased, then Ri is decreased more than the decrease in the Rm. Okay. So that is the advantage. The length constant is increased. When it is increased, we have observed that the length constant in 1 mm diameters axon of the squid is 13 mm. In mammalian nerve fiber, it is 0.2 mm. This nerve fiber is 1 micron in diameter. So increase in fiber diameter, the next point is increase in the fiber diameter. What it causes? It causes increase in the cm because it is directly proportional. Here rm and ra indirectly proportional, inversely proportional, and here cm is directly proportional. So increase in fiber diameter, what it causes? It increases the capacitance of the membrane. But this increase is proportional to the increase in the radius, while the decrease in Ri is proportional to the radius square, that is inversely proportional to the radius square. Therefore, internal resistance decreases faster than the capacitance of the membrane. The decrease in Ri speeds up the current to travel faster to the next region of the nerve, and threshold is reached sooner. So, the radius, that is the diameter of the nerve fiber, is relating to three important things, that is resistance of the membrane and resistance of the exoplasm. They are inversely proportional, and capacitance is directly proportional. So if you increase the axon diameter, capacitance increases, but Rm decreases, Ra decreases, and further it is very much decreased. So that if Ra is further decreased, what is happening? There is no resistance inside to travel the signal. So the signal will travel faster. Now coming to myelination. Myelin increases the conduction speed. How it can cause increase in the conduction speed? It increases the resistance of the membrane. That is Cm. It increases, that is Rm. It increases the resistance of the membrane. So this membrane is acting as insulator. So this is not allowing any current or any ions to leak through the cell membrane. So it increases the membrane resistance and it increases the lambda value, and it decreases the capacitance. How? By increasing the insulating layer. So capacitance is decreased. So there is decreased time to which constant of the membrane? Tau. So there is increased speed. So we have already seen that if there is increased lambda, decreased tau, then there is faster conduction. Okay. So exactly this is happening by our myelin sheath. It is causing increased lambda by causing increased membrane resistance, and it is decreasing the capacitance. So it is decreasing the tau value. And also our nodes of Ranvier, they will boost up the conduction or depolarization, because at that point only the depolarization will happen. So signal will be appearing as jumping from one node of Ranvier to another node of Ranvier. It is called saltatory conduction. Now coming to cable parameters. So you see here small rm. This is membrane resistance per unit length of the axon. Okay. R small r, it is extracellular resistance per unit length of axon. Small ri, this is intracellular resistance per unit length of axon. Cm, capacitance, membrane capacitance per unit length of axon. Now coming to capital letters. Capital Rm, it is the specific membrane resistance per unit area of the membrane. That is given by equation small rm, okay, that is membrane resistance per unit length into 2 into pi into small a. This small a is a axon radius. This small a is axon radius. Then coming to specific internal resistance per unit cross-sectional area of the axoplasm. This is given by small ri into pi a square. Okay, capital Rm is equal to small rm into 2 pi a. Capital Ri is equal to small ri into pi a square. Cm, specific membrane capacitance per unit area of the membrane. Okay, it is equal to small cm divided by 2 pi a. Okay, a is the radius of the axon. This is ohm. Is ohm into centimeters. Okay, ohm ohm per centimeters actually. Ohm. This much is the resistance. Resistance is measured in the ohm per centimeter. Per centimeter. This is also per centimeter. F is the Faraday. So capacitance is measured in the Faraday. It is measured in microfaraday per centimeter square. So here it is microfaraday per centimeter. So see the units. Ohm per centimeter. This is per. Ohm per centimeter. All resistances, these small letters, will be described in ohm per centimeter. In capacitance in microfaraday per centimeter. Capital R M is described under ohm into centimeter square. Ri is described under ohm per centimeter. Ohm into centimeter. Capital Cm units are microfaraday per centimeter square. Actually, this cable theory is based on Ohm's law and Kirchhoff's law. Here we can determine membrane potential at a specific position and at a specific time. Position is x and time is t. Membrane potential is Vm. Okay. So this can be derived by this equation. This is cable equation. T is time variable, x is the spatial variable, lambda is the length constant, tau is the time constant. This is known as cable equation. You already know this Ohm's law. I is equal to V by R. That is electric current is equal to voltage by resistance. This is the triangle of the Ohm's law. What is the definition of Ohm's law? The current in an electrical circuit, is directly proportional to the applied voltage and it is inversely proportional to the resistance. That is the Ohm's law. Now coming to Kirchhoff's law. In Kirchhoff we have two laws, current law and voltage law. So what Kirchhoff's current law is saying? Currents entering the node. Currents which are entering the node is equals to currents leaving the node. What is voltage law is saying? The sum of all the voltage drops around the loop is equal to 0. With the help of this cable model, we can simulate the spatial time-dependent expansion of the membrane potential on an axon membrane. This electrical circuit model and cable theory, they are conventional models. Okay. They are established model. They are established to explain and reproduce actual electric phenomena taking place in axon. But here you can see that the generation of action potentials in an unmyelinated axon is studied. It is now better understood that it is because of, that is, generation of action potentials is because of ionic transfers through many types of ion channels and resulting ionic concentration gradients across the membrane. However, these concepts had been not fully elucidated in the era of Hodgkin and Huxley. So they have said that our axon is behaving like an electric wire and how the electric current is generated like this, but they have not told about the ionic transfers. So here you can see the characteristics of ion channels have not told in these conventional models. But later on researchers have done. So with the present knowledge of physiology, we know that this is happening because of concentration gradient across the membrane. Okay, ionic concentration gradient across the membrane. And electrically charged ions are moving across the axonal membrane. In an electric circuit connected to metal lead, the electric carrier would be free electrons inside the metal. So in an electric circuit which is flowing, free electrons are flowing. On the other hand, in the axons, free electrons, okay, free electrons. So if you put these axon into a solution which is containing electrons, these are very much less than the our actual ion particles. And also the resistance of the cell membrane, that is lipid bilayer, is very much high, that is 500 to 1000 ohms per centimeter square. So our electrons cannot pass through it. So there is a difference between uh, actual electric circuit which is using a metal and axon. So new theories, new models, and based on these are based on recent studies. They are saying that a new conductive model they have created, and they are focusing on some points. So this conductivity is depending upon these points. What is this point? What are those points? Allow time lapse in one NAV channel, that is voltage gated sodium channel, and generation of action potential, ionic migration based on Coulomb force inside the axon from a viewpoint different from the conventional equivalent circuit model, ionic movement along the axonal membrane, and size of the axons, ratio of intracellular ions and inflowing sodium ion, density and distance of sodium ion channels on an axonal membrane, conduction velocity, and theoretical relationship between axonal diameter and channel density. So on all these points, the velocity of conduction is depending. We will see one by one. First one is the allowed time lapse in one voltage gated sodium channel. So what is that time? At each channel, elapsed time is less than 10 to the power of minus 6 seconds. So if you take an unmyelinated axon, the density of sodium, voltage gated sodium channels are 5 to 50 channels are present per micrometer square. So the distance between each channel is less than 0.5 microns. It takes more than 10 to the power of minus 1 milliseconds for an axon membrane to generate an action potential. So you stimulate one another fiber axon. It is taking more than 10 to the power of minus 1 milliseconds. In this time, in this time, there will be activation of more than 100 channels. Okay, more than 100 sodium voltage gated channels. So this means that the conduction would trigger the sodium channels. This the conduction will pass much earlier than the generation of action potential at, at each site of this channel. So this finding suggests that the propagation of the nerve conduction happens without the generation of an action potential. So mostly our electrotonic conduction happens like this. So action potential need not be generated, but conduction is happening. Why? Because it takes 10 to the power of minus 1 second to uh, it takes this much time to generate an action potential, but in this time more than 100 channels are opening. So these channels are opening up the next channels also. So there is no need to produce an action potential in case of smaller type of unmyelinated nerve fibers mainly. Now coming to generation of action potentials. So in the conventional cable theory, the membrane potential at a specific point, that is at a specific site and a specific time, it can be calculated by this equation. Okay, this is the cable equation. But in the actual sites of the internal surfaces of the axons, there is no closed metal circuits. Actually, these Ohm's law and Kirchhoff's law, they are based on closed metal circuit. But actually, in the internal surfaces of the axon, there is no closed metal circuit. So, in the actual site, under the steady state conditions, means with the no net effective transfer of the charge through the membrane potential can be calculated by an equation which is using gradient of ionic concentrations along the axonal membrane. This is GHK equation, Goldman-Hodgkin-Karch voltage equation. So this is ES equal to RT by F. F Faraday, T temperature in Kelvin, R is the universal or ideal gas constant, Ln, P means permeability. This is concentration. Okay. So out, in. So it depends upon the permeability and also depends upon the concentration of the particular ions. Okay. So that equation is particularly applicable when the steady state is there. Now we are breaking the steady state. That is, we are giving a stimulus. So it leads to development of some potential change across the membrane. Okay. Like it is producing action potential, for example. Then what will happen? Transfer of sodium and potassium ions will be happening. After the inflow of sodium ions at a specific NAV channel, actual change of ion concentration around the next channel is needed to make the membrane potential around that channel to surpass the threshold of membrane potential to trigger the opening of the next sodium channel. So what happens if you are stimulating at one point? Then at that point, at one level, that is at threshold level, the voltage gated sodium channels are opening. Then how the next channel will be opened? The next channel will be opened because of the incoming of the sodium ions from the voltage gated sodium channel. So at the next channel, there is a potential difference creating. This leads to opening of the sodium voltage gated sodium channel. So depolarization leads to opening of the voltage gated sodium channel. Further, it is leading to opening of the next channel, further depolarization. So this is leading to Hodgkin cycle. This is one of the most basic and invariable principle in the generation of action potential. Okay? But this is not fully reflected in the conventional theories. Okay? Because these theories are based on Ohm's law and Kirchhoff's law. Now coming to the Coulomb forces, ion and ionic migration around the next voltage gated sodium channel. In actual sites on the axonal membrane, the transmission of electric charges from one channel to the next is realized not by transmission of ion particles or free electrons, but how next channel is opening? Because of the Coulomb force. This Coulomb force is created by incoming sodium channels. So there is no need of making concentration gradient across the next sodium voltage gated channel. This Coulomb force is important. See here. Here you should learn about electrostatic repulsion and why it is disregarded in this situation. Because the voltage gated sodium channels will open for a very small time. The incoming sodium ions cannot they does not have time to repel the other sodium ions which are coming through the channel. So there is no point of electrostatic repulsion. So the total amount of sodium ions flow through a voltage gated sodium channel within the first T1. So if you uh, divide the total time into t1 like this. So first they can travel very fast. Okay. So this is constant. dq by dt is constant. So the electric charge which is flowing is given through this type of equation. So they will, the incoming sodium ions, they will exert Coulomb forces. So they will repel the cation because they are cations. This is given by this equation. And they will attract anions. This is given by this equation. So what is this? This is the ionic flux at a specific area in a specific time period within a fluid, because in the cell we have water also. So W is the molar mobility and C is the ionic concentration. So the total ionic migration velocity is given by flux by ionic concentration. So see, this ionic migration velocity is depending upon the Coulomb force. Now coming to ionic movement along the axonal membrane. So you should learn about dB length here. What is this dB length? Actually, so if you see cytoplasm or exoplasm, the charge will be balanced. That is, number of cations equal to number of anions. But strictly speaking, the cation anion ratio up to certain distance, that is up to 1 to 2 nanometer distance from the internal surface of the cell membrane, there will be anion denser layer. That is called dB length. That is anion denser layer from the internal surface of the axonal membrane up to 1 to 2 nanometers. That is called dB length. So why the dB length is important? The anions in the dB length, they will be attracted by Coulomb force. Okay. So the water molecules will hydrate some anions and some cations. Okay, they will cause deceleration in the ionic migration. See here, at the internal level of the voltage gated sodium channel, you have negativity charge. So positive ions are accumulated here. This is the dB length, 1 to 2 nanometers. And here you have more anions. These are water molecules. So the exoplasm out of the dB length is having equal amounts of anions and cations. So the exoplasm out of the dB length is not electrically charged. So see this Coulomb force generated because of ionic migration. That is mainly because of sodium ions migration. So sodium ions are coming. So they are accumulated here. They are attracting anions. Okay. Now this Coulomb force will travel like this. So first it is like this, then it is going up to here, then up to here, then up to here. So it is expanding in all directions, and it will trigger the opening of the next voltage gated sodium channel. Then coming to the size of the axons. In general, the unmyelinated nerve fibers are smaller than the myelinated nerve fibers. Usually, the unmyelinated nerve fibers will be 0.2 to 1.5, 1.2 microns in diameter. Okay. So by using this, we can derive cross-sectional area as pi d and cross-sectional circumference as pi d and cross-sectional area as pi d square by 4. So with the help of this, okay, if the length of the axon is L, then the area of the cell membrane is pi dl, and the intracellular volume is pi d square L by 4. Then coming to the next point, the ratio of intracellular ions and flowing sodium ion. It is depending upon the membrane capacitance. Okay. So the transferred particles to produce action potential is derived by pi dl divided by 1.602 into 10 to the power of minus 4. So ratio of inflowing sodium ion particles, that is sodium ion influx, is to intracellular cations is approximately equal to 1 is to 3.73 into 10 to the power of 3 into capital D. Okay. So intracellular cations are very much more. Then coming to the density and distance of sodium ion channels on an axonal membrane. So density is given by CD. Okay, density of these channels. The distance between two channels given by 1 by under root of CD. You see here, this is unmaintained axon. So these are the sodium voltage gated channels. Okay, if you spread this like this. Okay. So these will are in a line, that is channel line. We will call it as channel line. This is one channel line. This is next channel line. Number of these channels on one channel line, that is equal to d pi under root of CD. And the angle between two adjacent channels given by 2 divided by d under root of CD. Now coming to the conduction velocity. That is the time to take to conduct the action potential along a specific length. This is equal to T adjacent and numbers of voltage gated sodium channel lines along a specific length. So voltage gated sodium channels are very much important in conducting the action potential. And last coming to theoretical relationship between axonal diameter and channel density. Because axons, we already discussed that it has no cell organelles. This protein is actually synthesized in the neuronal body and is transported by kinesin protein. And this is also coming towards the axon with the help of microtubules. So the number of microtubules in axon is proportional to axonal cross-sectional area. So sufficient amounts of voltage gated sodium channels are expressed in the neuronal body in normal condition, so that the rate of gene expression does not affect or control this channel transportation to the efferent side. So there is constant recycling of the channels. These channels are synthesized in the neuronal body and transported by kinesin protein, and they are coming through with the help of microtubules in the axons. Okay, and these microtubules are proportional to the axonal cross-sectional area. So if the axon is more microtubules, more protein is present. So more rapidity of the conduction of the impulse. What are the factors affecting the conduction velocity? There are certain factors affecting the velocity of conduction. There are two main important factors. What are they? Factors which are affecting the conduction velocity are factors attributable to generation of action potentials. First, action potential should be generated. So, they depend upon temperature, level of resting membrane potential, and level of threshold potential or firing level. First, coming to temperature. If the temperature is decreasing, then the duration of the action potential is increasing. So, this delays the conduction. That is inverse relationship. Then, level of RMP. If the RMP is less negative, it slows down both generation of action potential and electrotonic conduction. When RMP is more negative, it slows down the generation of action potential but speeds up the electronic conduction. So the resultant effect on conduction velocity is variable but usually a decrease. Okay. So level of RMP, if it is less negative, what is happening? It is slowing down both generation of action potential and conduction also, electronic conduction also. If there is more negative RMP, it slows the generation of the action potential but it speeds up the electronic conduction. Then coming to the level of threshold potential, that is firing level. If the threshold potential is low, what is happening? The conduction velocity is increased and vice versa. Next coming to factors attributable to electrotonic conduction. First one is the axon diameter, second one is the myelination, third one is the resistance offered by extracellular fluid. First one is the axon diameter. So, in an unmyelinated nerve fiber, the conduction velocity is proportional to under root of d, where d is the diameter of the fiber. So, how it affects? Because it affects through Ri, that is resistance offered by axoplasm. Greater the axoplasmic resistance or internal resistance, weaker is the electrotonic conduction and vice versa. Okay. So, if axon diameter is more, there is more conduction velocity. Then coming to myelination. We all know that myelination will increase the conduction velocity. How? By saltatory conduction, and it will increase the axon diameter. Okay. And the resistance which is offered is high. Okay. Resistance offered by the membrane Rm is high in the myelination, and the capacitance of the membrane, that is Cm, is low. So Rm is high and Cm is low. And presence of nodes of Ranvier. All these three mechanisms will cause increase in the conduction velocity in case of myelination. So this conduction velocity equal to 6 times the axonal diameter. So this formula is the conduction velocity in meters per second equal to 6 times the axonal diameter in micrometers. Now coming to resistance offered by extracellular fluid, that is RO. That is resistance offered by extracellular fluid. It will also affect the conduction velocity. Greater the resistance, weaker is the electrotonic conduction. Usually this RO is small and usually remains constant, but it can also affect. If it is high, then it will lower the electrotonic conduction. Next video is about factors promoting the neuronal growth.